Now that we've got a hint of working with these trig functions and evaluating them at our degree angles, we want to get into the concept of radians, which is the more common angle we use. So before we can begin what that definition looks like, we have to talk about the concept of central angles and also arc length. So a central angle is a positive angle that has its vertex at the center of a circle. So if this is our circle and we have a positive angle, which would be this distance here, that is going to be our central angle. So this measurement is some theta value, which is the central angle. Okay. This circle has some radius, so that would be the distance here. And now this arc that is formed by the central angle is going to be measured in arc length. So if I were to start here at the initial side of that angle and I would walk along that curve, the arc length is the distance I would walk. So that we usually denote with an S, and S is our arc length. Okay. So when we define radian measure, it's really defined by a special arc length. So a central angle subtended by an arc length equal to the radius of the circle is an angle of radian measure 1. So this might seem a little bit weird, but the picture gonna be a little bit easier to recognize. So we have our radius here, we have the angle formed by this, and essentially the way we defined our radians is that when this arc length is exactly equal to R, then this angle here is going to be 1 radian. So in this specific instance, theta is 1 radian, okay? So what we're going to do to actually find the arc length, it just comes from really this formula. But the idea is if I keep going and I go 2R, then that angle would be 2 theta. If I go however many times around the circle to get my angle measurement in radians, I just divide this distance by that arc length. Because again, this is exactly 1 radian. So this is when S is equal to R. So my arc length divided by R gives me 1. If I go a distance of 2 radii, that would be 2 radians. And this would be my R, or my S being 2R. Okay. So if we call the arc length S, and the measure in radians of the angle theta, then to find our theta, we take the total distance we travel and divide it by R. So again, when S is exactly the radius, that's how we define 1 radian. So R over R gives me 1. If I go 2 times my radius, then my theta value is 2 radians. So really from this formula, from that definition of a radian, we get what's called our arc length formula. If you just multiply both sides by R, this gives you our arc length is equal to the radius of the circle times the angle. Okay. But it is important here that theta value does have to be in radians. Now this definition is great, but what we really want to do is find a way to convert from degrees to radians. So one thing you can think of, a full distance around the circle is 360 degrees. We're going to figure out what that is in radians as well. So we're going to consider a circle of radius 1, just to make life a little bit easier. So here's our radius, this is 1. And I'm going to consider making one full revolution for a theta value. So theta is going to be exactly 360 degrees. I want to see what that is in radians, okay? And again, I know my arc length here. I can just utilize my formula. My arc length is going to be r times theta, but my r is 1. So in this case, my arc length is exactly theta. So specifically, my arc length in this case is the entire theta value, which is 360 degrees, but this is in radians, okay? However, I do know a formula to compute this distance. It just comes from the circumference of the circle. My entire arc length in this case is the full circumference of the circle. So here, S is the full circumference. And if you don't remember what that formula is, the circumference is 2 pi times the radius. So ultimately, our arc length, utilizing our basic geometry formulas, is 2 pi times r. But in this case, r is 1, so my arc length is 2 pi. Okay? So what that means is my theta value is s, which is exactly 2 pi radians, okay? Because theta is measured in radians. So this gives me a way to convert it. This arc length is 2 pi, and that's exactly my angle value. But I also know a full circle is 360 degrees. So setting them equal to each other, 2 pi radians is exactly the same as 360 degrees. So ultimately, we know theta is equal to 360 degrees. So our conversion, we have two of them. 2 pi radians is exactly 360 degrees, or dividing by 2, pi radians is going to be 180 degrees. Both of these are conversions that are helpful for us. Okay? So to show you just with a nice XY axis, we know this is 0 degrees, 90 degrees, 180 degrees, 270 degrees, and then back to 360. Well, if I go a full revolution around, 0 degrees would be the same thing as 0 radians. 180 degrees is pi radians. And then if I go all the way around, I land back at 2 pi, because 2 pi is equal to 360. So this 90 degree is halfway in between 0 and pi. So 90 degrees would be equal to pi over 2. And likewise, halfway in between pi and 2 pi would be 1.5 pi, which is the same thing as 3 pi over 2, okay? So we're going to use this to be able to convert back and forth. And we're really going to work with these common angles really frequently. So you're going to see the same kind of numbers or denominators popping up over and over. So let's get some practice converting to radians. So we're going to start with degrees and convert to radians. So what I'm going to do is I'm basically going to multiply by 1. I know that pi radians is the same thing as 180 degrees, okay? So just like if you were converting from hours to minutes, you can always multiply by 1 hour over 60 minutes. The numbers are different, but it's still just like multiplying by 1 because these two are equal. And in doing so, degrees over degrees, that unit cancels out. So all that's left is I really need to simplify. We get 135 pi over 180. And then my only unit remaining is radians. Okay. So hopefully you're good with simplifying fractions, but this does simplify really nicely. So you can go ahead and divide top and bottom by 5 since they're multiple 5s, and then hopefully you'll see you can divide it by something else. Really, the biggest thing you can divide into both of these is 45. So 135 divided by 45 will give you 3, and then 180 divided by 45 will give you 4. So typically when we're working with degrees, we know we need this symbol here to indicate that. We don't write radians. If there's nothing else associated to it, it's in radians, okay? You can come up with a decimal approximation for this if you want, but again, circles tend to deal with pi. We're gonna have pi in most of our radians, okay? To show you with 270, which is really that angle down here, which I already showed you how to do because this is pi, this is 2 pi, so halfway in between those is 1.5 pi. 1.5 is 3 over 2. But just to show you with this conversion, again, same thing. Pi radians is equivalent to 180 degrees. So that makes that degree unit cancel. And you're left with 270 pi over 180. And then you can start by simplifying. You can divide by 10. That gives you 27 over 18, just to show you with this one at least. And then from there, they're really both divisible by 9. So that gives us 3 and 2. Okay. So 270 degrees is equivalent to 3 pi over 2. If you want to do the opposite, if I want to start with radians and then get it to degrees, really you're just going to flip what you multiply it by. So I'm starting with radians. So to get rid of radians, the pi component has to go in the bottom. And then the degrees in the top. Okay. And at least in this case, when you multiply by pi and divide by pi, those two cancel each other out. And then we can also do some more simplification all at once. If you want to take a step, you can. But this is negative 2 times 180 over 3. And then really 3 goes into 180, and you are left with 60. Negative 2 times 60, this would be negative 120 degrees. Okay. Now going on to 11 pi over 6, same thing again. I'm starting with my pi, so we are going to divide by it. The pi's cancel each other out. And realistically, I'm going to go ahead and do 6 into 180. That leaves you with 30 degrees. So really you end up with 11 times 30. So this in degrees is 330. Okay. All right. So let's try one more example, just utilizing that arc length formula since we had that here. And then we'll go ahead and we'll start talking about some other important concepts. So we are going to find the length of the arc made by a central angle of 120 degrees and a radius of 5 feet. Okay. So again, our arc length formula is S is equal to R theta, but it is specific. This theta has to be measured in radians because that's where our definition of radians came from. So currently my theta is measured in degrees, so I need to convert it. So starting with 120 degrees, I want to get it to radians. So I multiply by pi and divide by 180. Okay. Then both of those I can really divide by 60. So that leaves me with 2 in the top and 3 in the bottom. So our angle in radians is going to be 2 pi over 3. Now I can actually plug that into my arc length formula. My radius of my circle is 5 feet. Then 2 pi over 3 is my angle. So multiplying those together gives you 10 pi over 3. And then this is a length. So my unit is going to be the same unit as my radius. This is in feet. Okay. So you can plug this into your calculator, but you do 10 times pi divided by 3. It's about 10.47 feet if you needed an approximation. All right, so let's look at some of those important angles that we had with our triangles, because these are going to be really essential for us. I told you you're going to have to be comfortable knowing what sine of 30 degrees is, what sine of 45 is, cosine of 60, all of those core angles. You also are going to need to be comfortable doing that in terms of radians. So these are our 5 main angles that we need to know what all of our trig functions are evaluated at. This is going to be really helpful in building our unit circle as well. So starting out 0 degrees, you have no angle, you're gonna have no radians, okay? 30 degrees, you gotta multiply by pi over 180. So it'd be 30 times pi over 180 radians. Well, then top and bottom are both divisible by 30. So this gives you pi, and then 180 divided by 30 gives you pi over 6, okay? So this is kind of nice. 30 degrees, remember that deals with the 30, 60, 90 triangle. You have over 6 in the bottom. Gonna be equivalent when you have 60 degrees. You get the opposite number, so it'll be over 3 in the bottom. When we're working with 45, again, you're just going to times this by pi over 180. And then they are both divisible by 45. This will be pi over 4 radians. But again, you can also just utilize our angles. We know this is 0 degrees. This is 90 degrees up here, which is the same thing as pi over 2, okay? So if you want 45 degrees, it cuts this exactly in half. So this would have to be pi over 4 and pi over 4 to add up to pi over 2, okay? Then finally onto our 60 degrees. Again, times that by pi over 180. And then 180 divided by 60 gives you 3. So you get pi over 3 radians. So again, works out for 45. You have a 4, exactly the same number in the bottom. 30 has a 6 in the bottom, and 60 has a 3. So it's opposite. And then our 90 degrees, we've already done. But again, you times it by pi over 180. And then that simplifies to 1/2. So that is pi over 2 radians. So we are going to talk about our unit circle in the very next section, but if you know all of these different angles, you can find all of the other important ones in different quadrants. So again, once I know what my reference angle is, I know that sine of 30 degrees is 1/2. So sine of pi over 6 is also 1/2. I can then utilize that to find all of my different angles that have a reference angle of 30 degrees. The quadrant is just going to tell me whether it's positive or negative. So that unit circle is going to be super important for us, okay? Before we get to that, we have one last thing we're going to talk about. We talked about arc length, which is that distance. Now we're going to talk about the area of a sector. So if I have a specific angle and I basically just take a slice of my circle with radius r, we want to figure out what is that area it takes up. So we're going to call A the area of this sector. So if I look at the ratio of this area over my total circle, I can find that. And we're going to compare that to basically this angle to the full angle. Okay. So the ratio of the area of the sector to the full circle is whatever that area is, the area of a full circle is pi r squared, okay? But then what I'm gonna do is I'm gonna look at the ratio of this angle to the full angle. So the ratio of the central angle to the full rotation of a circle is, we take that angle, the full rotation is 2 pi radians. And again, this angle has to be measured in radians to make this comparison. Okay. Well, if you think about it, the ratio of this portion to the full area would give you some percentage. It should be the same percentage here because this takes up the same fraction for the full angle. So these should be the same proportionally. So what that tells us is if I set these two things equal to each other, we should be able to utilize this to find my area. My angle is known, my radius is known, so my only unknown is the area. So to solve for that piece, we just need to go ahead and get rid of this denominator. So I'm going to go ahead and multiply this side by pi r squared. So this way those two things cancel. But if I do that over here, I definitely need to multiply by pi r squared over here. So it does work out at least nicely. The pi's disappear. So this tells me my area is going to be theta r squared over 2. But really, that formula doesn't look so nice. So the one we actually use is dividing by 2 is the same thing as multiplying by 1/2. So it's 1/2 the radius squared times theta. And again, that theta is measured in radians. So all of our formulas come from radians, which is why when we get to dealing with graphing trig functions, everything is in radians. Those are the more common thing we use instead of degrees. But ultimately here, the area of a sector is, the area is 1/2 r squared theta, where theta is measured in radians. If theta is not measured in radians, you've got to convert it. You can absolutely come up with another formula for this, but I don't like memorizing another formula. Instead, just put it into radians. So if the angle is measured in degrees, just convert it to radians. No need to memorize a second, more complicated formula, okay? So let's try two examples of this. We're going to find the area of the sector given the indicated radius and central angle. So in the first case, our theta is 5 pi over 6, and our radius is going to be 13 feet. Okay. So if I want to find my area, it is 1/2 r squared theta. My radius is 13. This angle is already in radians, so I don't need to do anything with it. Okay. And then I need to take that radius and square it. 13 squared would give us 169. So that gives us 169 over 2 times 5 pi over 6. And then multiplying those, 169 times 5 will give you 845 pi. 2 times 6 is 12. And then it's an area, so your measurement should be your unit squared. In this case, our unit is feet. So this would be the exact area. And then I trust you could plug this into a calculator, and that would give you about 221 feet squared. And again, you could find the full area of the circle by doing pi r squared, but we're only taking this portion with an angle of 5 pi over 6. For this next one, the angle is in degrees and our radius is 9 miles. So the very first thing I need to do is I need to convert this to degrees. 30 degrees is one of our special angles, but again, while we're getting used to it, we just go ahead and multiply by pi over 180. Then if I do 180 divided by 30, that's going to leave me with 6 in the bottom. So this angle in radians is pi over 6. So our area is 1/2 the radius squared times theta. Our radius is 9, and then our angle is pi over 6. So 9 squared gives us 81. And then we've got to go ahead and times it by pi over 6. But we were working with 9s, that's a multiple of 3. I can divide top and bottom by 3. So if I do that, I'm left with 2 here and 27 here. So this would give me 27 pi in the top, and then 2 times 2 in the bottom gives me 4. And it is going to be my unit of measurement squared. So the exact area of the sector is 27 pi over 4 miles squared. If you want to plug this into your calculator to get an approximation, it's about 21.2 miles squared. Okay. So we are going to spend a ton more time in radians. Again, we're going to go ahead in the next section and talk about this concept of the unit circle. And that's going to tell us how we're going to be able to evaluate trig functions at all of these different special angles, which have reference angles of 30 degrees, 45, and 60. There is technically one more type of measurement for angles, which if you have a handheld calculator, you would see. It's GRAD to stand for gradients. Essentially, that's just a way to connect it to the metric system. So you still utilize the same idea, but things are going to be broken down into tenths to go along with that. Not something that's commonly used though, so we don't put a focus on it. Really, once we get comfortable with radians, that is all we're going to be used. We don't use degrees otherwise. Our trig functions are going to be defined when we get into an actual function as having radian input. So we are going to be working with these nonstop. If you're moving on to calculus, you are only going to be working with radians. You won't see degrees at all.